Okay, so good day to everyone. I'm Chu from MA Application Engineering. So today I will be presenting on the introduction to mirror surface machining. So about things like why it is required in the recent market, what are the end products, and finally what is the solution Makino is offering to our customer as of today. Okay, so based on rising market needs, more machining for plastic lenses, clear covers, HUD, medical tubes are increasing. Even plastic die mold for general products like pet bottle, phone accessories are also moving towards reduce to zero polishing process. Products that are minute and fine for medical electronics are also difficult to polish. Thus, direct milling to mirror surface finish is actually a key requirement for these types of customers. As you can see in these current slides, these all products are similar products that what our global customers are doing. In fact, application engineering played a significant role in performing all these test cuts on the various types of cavity or core molds. Take for example, this one and this one. We are talking about normal die mold products. We are actually more focused in the cavity regions as these surfaces are related to the visual, feel, touch to the end consumer. On the other hand, for plastic lens injection molding, hello, can everybody hear me? Okay, so on the other hand, for plastic lens injection molding, we are actually taking care of both the cavity and core finishing. So cavity and core finishing needs to be of a similar mirror finishing grade, as poor finishing at any one side, for example on the core side, will also result in a scrap lens product. So if I'm talking about plastic lenses, the optical quality of plastic is actually inferior to glass in terms of the dispersion, in terms of the hardness, the climatic resistance in terms of plastics will actually degrade over time, the stability in terms of the thermal and the moisture, so on and so forth. However, plastic is still very important. The plastic has actually a lot of important advantages in a way that plastic lenses are actually manufactured in large quantities like what we actually know by injection molding. So giving an example, if the cost for the tooling is actually $20,000, then actually we can actually reduce every part cost to even to a minimum of less than $1. So this is actually much more cheaper than those glass lenses. Not only that, it is half the density of glass, so it's more light, it's lightweight, and also plastic lenses have the ability to create complex shapes, aspheric optical surfaces like the light guides, PES lens, reflex reflectors, different geometries. We are also able to do diffractive surfaces like Fresnel lens, as you can see something like this. And also we can incorporate mounting features in the optic itself. For example, for this kind of a guide over here all the way until here, we can actually make something with a screw hole so that we can directly mount inside. So plastic itself have more possibilities. So if I were to focus back into the applications of automotive lighting, for example, reflex reflector mold, they actually are used to reflect light at night to make other road users beware of the vehicles. So it works in a way that it reflects the light back along a vector that is parallel or nearly parallel, but is opposite in direction from the light source, no matter where the incident light angle is. So there are actually a lot of requirements that is required when manufacturing this reflector mold. So you can see since light source actually comes out from here, the corner radius is actually an important factor to make sure that the efficiency is still kept to a maximum requirement. So corner radius, we are actually targeting at maybe R0.03 millimeter, or if maximum is R0.1 millimeter. Surface finish, we are targeting at 5 nanometer to 20 nanometer. So in this case, it's RA0.02 micron. Accuracy, we are talking about PV ratio. We are targeting at 1 micron. So for more information, what is PV, you can actually take reference from the files tab inside this channel. There's actually one slide talking about what is PV. This is actually one of the standards used for those light source industries, how they do the manufacturing. Okay, so these are standards. Okay, so based on the market requirement, the common voice is actually about achieving a mirror surface finish. And in fact, the skill of mirror surface finish varies a lot, from 5 nanometer, 1 nanometer to even 70 nanometer, depending on the customer level requirement. So certain customer will say, oh, I want mirror, but do they know what is the skill they want, which is good enough? Because every skill itself also determines the machining time, because the AP and the AE, the step of the machining is also changing, depends on the process. Okay, so for most lens cavity mold, we are actually targeting, and other products we are targeting at RA20 nanometer in average. So take a look at the mini pocket sample. This is actually achieved at RA20 nanometer surface roughness. Okay, this machining surface is actually produced by direct milling process, which is actually by IQ machines. Let me also introduce another machining sample about mirror surface finishing. Okay, this is a PES lens. PES is actually called polaric ellipsoid system. This is a type of non-circular lens geometry. You can see it's like hemispheric, but there is a certain formula inside. So it's actually non-circular. This is actually used in LED light sources for automotive headlights and also HID systems. So normally the machining process goes like this. First off, we actually perform roughing on the material, and then we do a semi-finish so that the rough shape is there, the net shape is there. Then we actually add a layer of a plating, chromium nickel, or maybe other substances. And then with this plating that is on the surface, we actually do a finishing and maybe polishing later on if required. However, nowadays with IQ Micro Machining Center, we can actually perform direct milling from roughing to finishing with this Stavex material with such a high level of surface finish. Okay, so this is achievable on direct milling process. And the reason between why we do not want to use direct polishing, maybe it will be even faster. However, when it comes to certain formula that is required to do the reflection and efficiency of the light sources, just doing a polishing may actually affect the formula and the surface of this geometry, and thus this will actually affect the efficiency and certain lighting effects. So for this presentation, I will just give a very simple explanation in terms of application wise. Okay, so for more information regarding like how do we do the machining from modeling and all this, we actually will trace back to, if you have a customer inquiry and all this, we can actually discuss further. So this overall PPT is more on raising the awareness that Makino machines are able to achieve this kind of processes. Okay, so this is just an introductory explanation on mirror surface machining concepts. As you can see here, in order to achieve this kind of a surface finish level, we are actually doing the final machining by PCD and mill, ball and mill, in fact. So it is like we call it a milling, but if you were to zoom into the tools, you can see that there's actually no visible cutting edge on the tool. It's like a solid ball, and then it's actually rubbing on the material. So I can say it's something like a burnishing. So it's a little bit of a pressing to form this surface that is shiny. So in order to do so, we need to make sure that the machining overall process only cut 1 to 5 microns depending on the cutter, depending on the deformation, based on the rigidity of the tool, as well as the surface, as well as the material that we are using. Many parameters comes in, but the range is from 1 to 5 microns. And because of this, it is not like our conventional machining process whereby you say, let's do a finishing 30 microns, 25 microns, 50 microns every cutter, it will still cut. But in actual case, can you confirm that the cutter is cutting 25 microns? You cannot confirm. Why? This is actually due to semi-finishing process. Are you actually cutting to the same amount of stock that you desired, that you intended? The next thing is whether your cutter size is it exactly R1 mm or is it 0.994, then a few microns differ. What about the overhang? What about the run up? Everything varies in. So when you say you actually do a normal machining of 25 micron stock, maybe you are cutting more, 26, or you are cutting 20. In this case, maybe something's the height of the tool is wrong, the compensation is wrong, so you might not be cutting exactly as 25 microns. So if we actually jump back to the machining aspect for 1 to 5 micron, this not only means that on the process wise, application engineers need to understand that the setting of the workpiece and the tooling is very important. Another important aspect is actually the thermal displacement of the machine, how machine is stable, how machine spindle is strong enough to take care of the vibrations, mechanical vibrations. What about the assist fit motion? Is it smooth or not? Are we using ball screws motion to drive the whole movement? So these are things that we need to consider in terms of machine selection. And the key point here is depending on the surface of the machining area, the bigger the surface, the finer the machining surface you want it to be, the machining time can range from 50 to 100 hours. Of course, there are small parts where you just need 1 hour, 2 hours, but if you are doing bigger molds, it can range up to 100 hours or so. For this part itself, the surface finish required is not that high. Is around like RA maybe 30 nanometers or 40 nanometers. And because of this big machining area, it actually takes up 63 hours of machining, just the finishing. Okay, we are not talking about the roughing. So just the lens itself with the light guide, it takes around 63 hours. So imagine the machine rigidity and capability is actually also important. So just giving by example, Makino have IQ series machines, IQ 300 and IQ 500. So these are actually used to target micro machining applications as well as mirror surface machining applications. So some of the key points that I have mentioned just now, first off is spindle technology. So Makino spindle for this IQ machine is 45K RPM. Okay, we are using a tool shank of HSK E32, which is relatively small. Okay, and then important point of this is we also develop the spindle in a way that mechanical vibrations are reduced to a much extent, and then application engineers also have the responsibility to understand the spindle characteristic and at which point of the spindle RPM actually can result in a lower mechanical vibrations in terms of the natural frequency of the system. So from there we are able to reduce further vibrations. For fine control, it's actually about how the axis is being moved, driven. So for IQ machines is actually different from all our machining models, milling models. We are actually using linear motor to drive it. So mechanical backlash issues and certain vibrations are reduced. Okay, and then next point is also that the guide itself, we are not using standard linear motor guides. We are using roller guides, precision roller guides. So it actually further helps to improve the control system, how we actually move. The feed axis accuracy is also being increased. We actually have scale feedback of 1.25 nanometers in all axes. And the programming unit in this controller system is actually another 10 times lower of our standard machines. So normally our standard machines goes to decimal of 4 points, which is 0.1 micron, but this one is 0.01 micron. So programming point of view, we are able to make it more precise to actually deliver this kind of product. When I actually say about linear motors being able to reduce a lot of mechanical vibrations and extra errors, another one thing on the back end for linear motors is they actually generate a lot of heat more than the ball screws. So temperature stability is very important. For that, IQ machines has been designed in a way that we have a controlling system to just cool down the spindle system. We have another automatic system to cool the feed axis for XYZ, and then we have another one for the coolant temperature controller. The reason between having these three and combining it is actually, of course, cost driven is more expensive, but we are able to control every system specifically more accurately. And because heat generated at different zones is different, so having different controllers at each systems can help to make sure that every of these systems are well controlled. Okay. So besides the machining point of view, the tooling is also very important. So when I say about the PCD cutters, it's actually called polycrystalline diamonds. There are several of these tools that are actually available in the market, like NS Tools, Mitsubishi Hitachi, so on and so forth. And this is actually made out of the diamond grain and the binder. If you were to see from the so-called microscopic view, actually diamond grains size is important and it actually varies from different manufacturers. Actually, the smaller the diamond grain, the finer it is, actually it can produce a better surface finish. And the formula of the diamond grain size is actually kept confidential by the makers, so they will not let us know. Okay, so in average, we actually have a comparison of understanding which maker have a better quality, but this is actually more on the composition. The final machining surface of the tooling also stands out. So what do I actually mean by this? This means that even though we have a good machine tool and PCD toolings, we still are facing certain limitations. We actually are able to produce mirror surface, but as you can see from this picture, sometimes the mirror surface are showing rainbow marks. And these rainbow marks are actually some phenomena that we actually see through our eyes. This is being reflected from the surfaces itself, and different colors actually shows that light is being reflected at different wavelengths to our eyes. So this is actually caused because the cutter itself is having a bad R accuracy, and this R accuracy is due to the grain size and the composition itself. It's not being well machined. So at the end of the day, this reflects back on the surface and we see these rainbow streaks. Okay, so this is the limitation to the R accuracy. For normal ball and mill accuracy, we are talking about plus minus 5 micron. This is actually for standard cutters, like in Japan made. If we are talking about 20 microns, oops, it can be up to 20 microns or 10 microns. And then for premium cutters, if you actually buy with certificate, they can reach up to plus minus 2 microns for new models. But this is still not enough. So with this 1 to 2 microns error for all surfaces, this 1 to 2 microns error actually will cause a 0.5 or 0.6 micron gap, and this actually causes that lights to interfere and show you different colors based on different wavelength. For example, 300 nanometer wavelength is 0.3 microns, so on and so forth. So we are trying to reduce the R accuracy error. This is the main point to achieve a better mirror surface finishing. So based on this current limitation, Makino managed to develop this many years back. We call it the MSFS. Oops. Okay. So what happened here is we actually wanted to implement in-machine truing. Truing actually means like a dressing. It's a term to dress our PCD toolings to make sure that it can have a better R accuracy. So the meaning of actually doing this truing in the machine, and after which we can directly do the machining, this is actually the main goal of it. So let me talk more about mirror surface finishing system, MSFS. Okay, so mirror surface finish system, this is a solution that we provide to users. This is to perform the truing of the tools during rotation. When I'm saying about rotation, it means that the truer wheel, the white color circular thing, is actually rotating at a formula speed, as well as the tools itself. So tools are rotating, the truer wheel is also rotating at the same time, and we do the dressing. So the machining by tools where truing was performed helps to enable a better finishing of mirror surfaces. I can say that PCD tools itself can actually produce mirror surfaces. However, we are actually improving the mirror surface quality. And this is patented, and this is our machine option. So most of the machine models that has been sold worldwide, I believe more than around 50% of the machine models are equipped with this option, because this is one of the this is some solution that Makino is proud of it. So this is in-machine truing of PCD tools. You can see it's actually on the left side. This side is actually the ATC panel. So tools actually comes in from here, and then we can do the machining, the truing, and then after which we can do the machining at this root zone. If we look into specifically, this is the truer wheel. Actually, it comes with two different sizes depending on the diameter of the cutters you're using. Same as grinding concept, the bigger the truer wheel, the better the grinding effects. However, because if you are doing the truing of smaller tools, it may result in an interference, which means collision. So case by case, sometimes depending on the customer application, we will say, oh, you can just buy truer wheel A, the size of 20 diameter, something like that, or 40 diameter, and then you just skip to this, because by actually interchanging between two wheels, it take a long time to set the center of the wheel and to do the dressing. in case of a new wheel or something like that. So it's actually case by case. Next, we have a nozzle. You can see there's a two fixture here, one and two, left and right. One is actually blowing the special mist that actually helps to do the lubrication during the dressing, and the other one is actually the air to blow away the powder and chips. This is the chewing unit. It's developed by Makino, similar to a spindle drive system, and this is cooled by oil air, if I'm not wrong. And then on the back end, you can see it's a PTIM unit. Okay, this PTIM unit is something similar to a ATRM, like a laser. But what laser does is they actually detects the tool when the laser signal is being blocked. So the receiving end cannot receive the signal, and they know that this ATRM is triggered. But for the PTIM unit, it's actually called Precision Tool Imaging Measurement Unit. It's actually measured by optical systems. So the tools actually will move in exactly to this position, and we will actually do measurement to actually understand that oh, this tool looks like this and that, and then we will focus and take some time. So cycle time actually is around 1 to 2 minutes per tool, depending on the function that you want. Is it just tool length measurement or with the diameter measurement? So it's a case by case as well. So all this unit is important because not only the PTM unit, we need a high precision AWM unit to measure the thrower wheel. We also need to measure the dressing unit. There's several things that we need to measure on the PTM unit to confirm that before dressing and after dressing, everything is made precise and accurate. So later on, I will share with you about the process. Okay, next off, there are definitely limitations on the tools that we can choose. We can only choose PCD, mainly PCD and mills. Of course, CBN is possible, but we do not encourage because they are cutting edges. So by doing so, maybe cutting edges might be blurred off, and this defeats the purpose of using CBN cutters. So mainly we are targeting on PCD cutters, which is polycrystalline diamond tools. When we are talking of ball and mill, we are targeting from R0.2 to R1. So several makers actually cooperate with Makino MSFS system in a way that they already proven that their tools will not crash with our system because they have already designed it to be this way. They actually bought this system and test it on their site and designed this cutter for us. And the other one is actually taper ball, but however it is still not very recommended unless certain special applications. For more information, you can just text me and I can explain. So what are the three main points that MSFS system can benefit? First is the runout accuracy. Of course, on the operator point of view, we need to make sure that runout is well controlled at shank within 1 micron. This is the first requirement. However, based on different RPM rotation, dynamic runout still exists. So by doing the chewing operation on the MSFS system, we can theoretically ensure that dynamic runout is at 0, and at this same condition where rotation is being performed, we can directly do machining. Okay, so this is the first benefit. Second benefit is what we are talking about, the R accuracy. So R accuracy actually varies from makers as well. Some makers actually have developed through the years their R accuracy is much more better 5 years than before. So sometimes without using MSFS, we can still relatively get a good surface finish depending on the surface profile. For example, if you are cutting a flat surface, you will be always using a certain point. For example, you can see an arrow here. If I'm cutting a slope, which is a straight slope, always I'll be touching one point. So there's no meaning and no definition about what is a two profile accuracy, because you'll be using always 1 point. Okay, so for complex shapes, there's definitely importance in doing the truing process, and depending on the maker, some makers are having a very bad R accuracy. So truing process from MSFS systems helps to improve the overall accuracy to within 1 micron. And this is also subjected to the composition of the grade that the maker is offering. And the next thing is also the roughness of the tool. Imagine from an EDM operation, if the surface roughness of an electrode is very rough, the final process imprinted on the surface will not get any much better. So same thing on the parent tool, we need to make sure that roughness of the tool is being well controlled. So we are able to improve the overall surface roughness of the tool, and because of this, the overall surface quality, the mirror surface quality on the mold itself can be further improved. So these are the 3 main points that we wanted to highlight. Okay, so this is the overall MSFS process that can be automated by using the macro programs. So everything has been well prepared. You just give the program to the customer, they can press a cycle start, they can do roughing, semi-finish, MSFS operation, and then directly to finishing. And this can be run during weekends and all this. So it is not a big problem. So first off, what is happening is we will call a Renishaw AWM to measure the wheel, to understand how much is the size of the wheel. And then we will actually also call the dressing cutter. As you can see on the second picture, this is actually a dresser to dress the wheel. So this dresser itself, first off, we need to make sure that the condition is good, and we also need to know the correct tool length compensation to dress the truer wheel. So the dressing cutter will actually go to the PTIM to do the measurement and the diameter. Actually, diameter is optional. Important is the tool length. Then after which this dressing tool will do the dressing. After the dressing is done, we need to confirm the size of the truer wheel again. So we will actually go back to the first picture. Okay, the AWM will actually take few points along the profile, get the average dimension to confirm that we already sized the truer wheel. Based on the finalized dimension of the truer wheel, we will get our cutter in. In order to do the truing, we need to make sure that we got the correct diameter of the tool, the PCD tool. We need to know the tool length so that we can do the correct compensation. If not, it will crash into the system. So all this has to be measured on the PTIM unit first, and then we will do the dressing. So this truing actually consists of 2 different types of process. One is a roughing truing, another one is a finishing truing. So for roughing truing, we actually will do it roughly to rough off the whole size, because we need to make sure that the whole size is being roughed 3D in 3D dimensions. For example, this is the R1 diameter, R1 radius PCD tool. We actually will make sure that it is removed in terms of into R 0.995. So every 5 micron in 3D space is being machined roughly, and then we actually need to proceed with finishing. However, because of the rough truing process, we actually result in a wear in the truer wheel, and this actually goes back to this point again. We measure the dressing wheel, we redress the truer wheel. After the truer wheel is confirmed, we remeasure again the truer wheel, and then we do the finish truing. So the roughing and the truing process is a little bit different, because the truer wheel itself, if you were to see from top, there's a thickness of maybe 10 to 20 mm millimeters. So for roughing, in terms of performance, we will actually do the truing in a sense that is the tool is circulating around the profile of the wheel, and at the same time y-axis is moving, so that every of the part of the truing wheel is being used to rough up the material. However, when we are talking about finished truing, we are no longer machining the 3D space. Okay, we are actually machining in terms of z-axis up, so that only tool length is updated. The tool radius is always the same, because we don't expect the cam side to keep changing the diameter. Okay, so only z-axis is changed. And also, in order to achieve a higher accuracy for the finish profiling, we only do in a way that y-axis is not moving, so that we can get the maximum accuracy of the truer wheel. So there are different types of truing operation, in fact. And finally, after all this is being done, the tools itself will go back to the PTM unit for final measurement. And this final measurement will be the value when rotation, and this will directly be used for your machining. So tools is always in continuous rotating operation. So run out, surface roughness, everything can be controlled as per the ideal state. Okay. So I hope you can see this video. We are doing something like a AWM measurement. Okay. Then this is like a dressing. Okay. And then you have things like truing, the process, whereby both the tools and the wheel is rotating. Okay. So this is the concept of how MSFS works in machine. So once this is being done, we are able to realize the three benefits that MSFS can provide. So this is a rough surface comparison of the tool. Before machining, before doing the truing, we can see that there's some porosity and some inaccuracy in terms of error. So imagine if we are doing the direct machining with untruth tool, you actually will have problems in the error accuracy up to plus minus 2 microns, 3 microns. But if you do the truing operations, you can make sure that your overall dimensional accuracy in 3D space is well controlled within plus minus 1 micron. So just a important consideration to take note is, if you were to perform mirror surface finishing in terms of customer or application engineer, there is a need for metrology systems. Only with certain scopes and vision measuring systems, we are able to define how well we actually perform. Is the surface good or not? Is the mirror surface finishing really good? Because based on eye level inspection, for certain customer it may work. For certain stringent companies, they actually go through light testings, make sure that the zebra stripe lines are well controlled and all this. So things comes in whereby we need to measure and cut and to monitor, and then to analyze is our cutting process correct or wrong. Okay, so this is a quick example on a spherical lens mold. Actually, this spherical lens mold is quite small, diameter 16 by 30 mm height. The spherical formula is SR10, so it's actually a radius of 10 mm. And we actually used it can be machined by FFcam and even some other special calculation systems, because it is done by formula. And we actually make use of a PCD cutter to do this finishing within 31 minutes. Actually, it's quite small. Okay, and we are able to achieve RA 7 nanometers. with a 3D accuracy within 1 micron. If you were to take a look at a comparison between a normal cutter and a cutter that use a MSFS, you can see that the lines are very visible. These are actually done by those non-contact lens measuring systems. You can see lines over here that's red color. It actually means 0.5 micron kind of a cut. So it can be is mainly due to the tools itself. So at different regions, the contact points is different. The grain size and the composition actually makes a difference in the final quality. If we actually use a contact type to do the measurement, we can see that there are several spikes here and there during the peak feed direction, which is up to around 400 nanometers, 0.4. Final surface roughness over here, you can see RA for normal cutter is achieved at 86 nanometers, is around 0.08, which is quite good, RA 0.08, but this is zoom in particularly, so you can see certain lines, which is not acceptable. For the MSFS surface, we can able to achieve 16 nanometers. So by using MSFS to crew the PCD toolings, we are able to improve the overall surface roughness by 5 times, which is 1/5. Okay, so this is actually the end of the overall topic that I want to introduce about mirror surface finishing. But now I will just roughly show 3 samples that has been machined in Makino Tokyo. So these are just some case studies for you to see what are some of the relevant molds and cavities that we are able to achieve. So this is a reflector and light guide combination. Normally people don't do like this, but we try to combine it as one sample to show customers that we are able to machine reflected lens and even light guide systems. The requirement for these two features are a little bit different. In case of the reflected guide, the reflected lens, the requirement for the surface roughness is much more higher. We need to make sure that we can achieve a RA of 30 nanometer and below. This is actually done directly on the IQ 500 machine, and the overall time is 93 hours from the semi-finish to finishing. So the roughing is actually done on another machine, which is F3. For the light guide itself, surface roughness is not much a requirement, but in order to ensure the maximum efficiency of the reflected radiation, the radius is an important part. We need to use R 0.05 mm cutters or even R 0.03 mm cutters to do the machining. So the cutter size is important, machining parameters are important as well. We only cut 5 microns to 3 microns per depth, but however, if the machine is not stable, we will actually cause either air cut or the cutter will break for a long period of maybe 5 to 6 hours just for this script for corner radius machining. Another thing is with the capability of the PTIM system, using the optical systems, we are able to do easy measurement, accurate measurement on the small tools. For more on the information on PTIM, we will be actually do a preparation for these materials, and we will most likely release as per a standard online learning session in the next month or so. Okay, so this one is the PES lens. This is the polaric ellipsoid system. So this is done on a 52 HRC material. So in fact, what happened here is material also makes a big difference in mirror surface finishing, because depending on the material grade and the hardness of the material, um, the burr formation is actually different microscopically in different machine materials. So on the application point of view, we will also encourage or recommend customers and users that what kind of material grade they should be using for maximum quality of mirror surface finish. So in this case, we are actually using FFCAM for 20 hours to do this machining. And then in the later part, for certain kind of molds like this, we actually use other kinds of machining techniques to improve the overall machining cycle time. Because what actually happens for this kind of typical lens is that the radius in terms of a 2D profile is very big at the start of the machining profile. And at the end of the profile, if you were to do a contour spiral machining path, the radius actually gets smaller and smaller and smaller. So the axis reversal, even though there is no ball screws driving its linear motors, there's also an effect on the servo motors that you are actually constantly changing the axis, especially at the bottom regions, is getting worse and worse. So there is a possibility that we have to change another alternative to better control the feed rate at different levels. So this kind of NC programs can be actually generated for better machining efficiency and as well as the dimensional accuracy. Because if we are running, for example, 3000 feet rate or 1000 feet rate at the bottom area, it is not effective, because first thing first is not running at this actual feet. At the same time, the overrun of this feet actually cause scratches as well, or even some waviness due to servo incapability to follow these commands. So this is another one. Next one is actually a reflex reflector mode that many customers do. It can be in circular, it can be in rectangular shape as well, depending on the customer. Sometimes it can be in matrix. The pattern can be different in a way that the first half is facing front, the other is facing back, so that the shape is actually tilted. So when we are doing this kind of products, we actually will actually have to take note at the customer angle, the angle of the reflector shape. Then this will actually finally determine our end finishing tooling that we need to use, as well as the corner radius. So the bigger the corner radius, of course, this helps us in a way that we can reduce the number of toolings to do the corner arm machining. But when it comes to R 0.03, then it means that we need to have a R 0.03 cutter. We need the R 0.05 for corner radius machining. We need to step back upwards. We need the R 0.075, R 0.1, R 0.2, 0.4, so on and so forth. So more cutters are required, more machining time are required as well. The key point for this machining is very simple, because it is just a tapered surface. So we will not have much influence on the error accuracy as what I have mentioned. However, by doing 240 hours of machining with a particular tool at a single point contact is very difficult to do, not only for the PCD cutters, but as well as the semi-finishing tools. So imagine you are using a CBN cutter to do the semi-finishing. You actually will result in a surface, you will result in a tool wear at that particular point instantly. So cutting parameters, in especially semi-finishing, is very important in this kind of applications. By actually managing the tool wear, then we can only confirm that the final finishing allowance for the whole molds are well controlled. For example, I said I want a 2 micron stock. So I need to make sure that all surface are controlled at 2 micron stock while using CBN tools. It's a very difficult process. So it's a very tedious process on how we need to manage it. And then we will actually do the finishing once the semi-finishing is finalized with uniform stock. So other than that, in case of smaller radius cutters, this also means that we have to we need to ramp up our spindle RPM. So there might be applications that we need to use an air turbine spindle. It's actually like an extra attachment to the spindle to ramp up the spindle speed up to 120,000 RPM. There are 80,000 RPM, there are different models. So the working mechanism is the way that spindle is not moving. The 45K spindle is not moving. We actually put in a holder, and this holder will rotate by air. So with this pressurized air, well maintained at a certain cooling temperature, we actually will do this final machining. So all these things are actually done with the MSFS as well. So there's a lot of separate technologies that are of different modules that are being combined together to achieve this thing. So it's actually very complicated. So for more information about it, we can actually start off with a customer inquiry, understanding that there is this certain request. Then we will work closely to understand what are the first step, second step that we need to do, what are the resources that customer need to prepare. Then I think this should be a right way. Okay, so this is the end of my presentation. The main thing for this presentation is not to increase your application skills on mirror surface machining, but to raise your awareness that we are able to realize this machining process in Makino IQ machines. Okay, thank you. If you have any questions, please type it out, and maybe I can try to give you some answers. Okay, Mr. Yu Li Hong have a certain questions on the chewing process. Normally it will take around 15 minutes to 20 minutes, depending. Of course, we can help to further reduce the timing, but it is not a very important thing for customer because most of the time to do a mold, it takes 100 hours to 200 hours. So 15 minutes is negligible. And depending on the different kinds of PTIM models that has been in place for different machine models, the micro programs for measuring differs a bit. So there might be a little bit of a plus minus 2 minutes, 1 minute. Okay, number point 2, what is the recommended RPM for chewing process for both spindle and chewer wheel? This is actually a very good question. Chewer wheel RPM is well defined inside the system, so it is actually a formula RPM. We should not try to disclose it, and this is actually well related back to the grinding principles, and there's a lot of test and trial errors that the development team has tried out. So for the chewer wheel RPM, it will be automatically controlled based on the roughing and finishing conditions. And then for the both for the spindle condition, it really depends on for that particular application you are doing for that particular material, what is the spindle speed that you should be using. So for this more information, I will try to provide later on in case of mirror surface finishing test card requirements from regions, then I will let more people know about it. And mirror surface we've compared with manual polishing, how long will it take as compared with direct milling? Actually, case by case, because different surface, for example, a big surface, for normal general molds, they can just do manual polishing because First of all, surface finishing will be good. Dimensional accuracy in terms of 1 to 2 micron that is being sacrificed is not a big important point for the customers. Then they can do with manual polishing. When customers manual polishers are going to retire soon, they are actually having a lack of polishing workers, or they are unable to implement automated polishing. Then they will actually slowly have inquiries whereby, can I actually do direct milling so that I can reduce this kind of work? In case of, as what I have mentioned in the PPT, for special products whereby surface accuracy is important, and then with the parts are very small, there's no way for manual polishing, then IQ actually comes in to tell you, hey, we can do everything in one shot. So it is case by case. Second point, what is the surface finishing required before proceeding with mirror surface process? I can say surface finishing is not a very big important point, rather than we need to focus more on the uniform stock. Because if the wear is too much, normally we are talking about 10 micron, 20 micron wear, and that is the problem. Because if there's a 20 micron wear, maybe at the start your PCD is cutting 5 microns is okay. At the end, your PCD is cutting 25 microns. Then if you are cutting 25 microns, depending on the cutter rigidity, it is actually more than a rubbing. It's actually creating more pressure on the tools. The tools might break, depending on the size as well. And then the cutting load is too much, extra vibrations comes in, surface might not be good. So I think this is finished for you, Lee Hong. Next up for Lee Santa Maria. Does our competitor have similar solution like IQ series? Do you know their solution concept? We have a few competitors. One of them is like Toshiba Machinery. Recently, they merged with another group, so I forgot the name. But what happened for them is they are using air turbine spindle, something like our air attachment spindle. So they are having a great, or I can say a better finishing than us. Definitely, because there are technically no mechanical vibrations due to the air-driven spindle. However, because it's air-driven, it also means that the spindle rigidity to do machining is not there. This means that, for example, for certain lens, they need to do a machining on other machines, semi-finishing on another machines, and they need to make sure that when they actually put this part into their machine, they need to have a uniform surface as well. And by doing the setup is very tedious. So for IQ machine, we are able to do most roughing applications, one shot, one setup. So this is actually our good point. We do not make it in a way that we are using purely air turbine, but we are able to have a combination of a mechanical spindle as well as a air attachment kind of thing. So this is the difference. Okay, I think this is and for Lee Santa Maria, and then for Chaitanya, is it possible to achieve mirror surface finish on F and V? It's possible actually technically, because if you have the toolings, you got the correct parameters, you can do the mirror surface machining. Important is actually the application process and the customer technology level, their skill level. Because since I'm talking about 1 micron, 2 micron cutting, you need to make sure that your machine is able to control within this region. And then what is important point over here is that for better in order to achieve a better quality surface finish using PCD tooling, we actually make use of oil coolant. So when we are using oil coolant, this also comes in a way that the machine is subjected to cooling, and we cannot control the temperature, stability of the machine. So, and also subjected to the profiles that we are cutting. So if you're talking about you are cutting a borehole, like you can just do a boring, but if you're doing a borehole, doing a PCD tool, you can achieve a mirror surface finishing easily, because even though you have Z deviations, it will not affect in overcut or undercut kind of thing. So it's possible, but it really is really subjected to a case-by-case basis, and how you need to make sure that the stability is being well controlled. Okay, so for Vijaya, what is the step over in using my finishing operations? It depends. Varies from 2 to 2. The smaller the 2, the smaller you need to cut. So normally for R1 is actually you can go up to 5 micron to 5 micron APAE. For smaller tools, it can be 1 micron, 2 micron. Sometimes I try 0.5 microns, but 0.5 microns cutting over 50 hours sometimes might not be working great, because 0.5 micron actually means 500 nanos. So easily we can see certain spikes over like thermal and all this. Okay, then I go back to Satish from MTTC. How are we getting an RPM of 120,000 during semi-finish and finish? So as what I've mentioned, this is actually done by using a air turbine spindle. It is not the spindle of Makino machines. We actually buy it from Big Ajoa or maybe even more other models. So we need to put this thing in. We actually have a option that we can supply direct air to this air turbine system. So it also means that semi-finish and finishing operation, you need two holders, and then you actually use collet to clamp it in. So we cannot control whether you want 100,000 or 120,000, because based on the air pressure, it should be fixed and constant. The main important point for air turbine system is if you get it from the Makino is key point, because if you are cutting with a small cutters, what is important is thermal stability and the pressure value. Because for example, if you are doing a machining and after a certain time along the line of machines, some are doing ATC, then if there's a sudden pressure drop in your air supply, suddenly your air booster will become like a 80,000 RPM during the 50-hour cycle. And if it's a 80,000 RPM while we are using the same feed rate, it means that your feed per tooth is increased, and this will damage the cutter. So for Makino solutions, if you buy these options, we actually have an air booster to make sure that air is controlled at a certain pressure. Same thing, air itself also have temperature variations, so we control the temperature so that there is no thermal displacements due to the air. And lastly, the air itself that's going through, for longer maintenance of this unit, it has to be clean. So we have an air filter for this one also. So it's not that straightforward. Okay, so this is done for Satish. Lee Santa Maria. How long you can use the PCD tool that you can chew before chewing again? Actually, what happened, there are different kinds of applications, and it's difficult to judge. So for example, if I'm doing a reflector mold, the worst case, whereby every time I'm always contacting one point, because this is a taper surface. So what happened here is I can use for 100 hours, and the wear is less than 1 microns. So for better quality, we don't actually do it in a way that we say, okay, we can still continue to use it because there is less than 1 micron error. We will chew it again to use it. We need to chew it again before using it for the second round. So because of the chewing process, the underlying benefit for MSFS is we can reuse the cutter. So For a normal PCD RL radius 1 mm tool in the market, it costs around 50,000 commercially, 50,000 yen, which is around 600 Sing dollars. So by using one time for a certain contact surface which is already wear off, we cannot use it anymore unless we are using for the different surfaces. But however, if you have the MSFS, we can do more than 20 times. We actually recommend it to be like within 30 times, depending on the size of the cutter and the overhang, because this PCD tools itself is a complete composite, so we can regrind it kind of thing. But by able to, in a way, by using MSFS, we are able to throw it in a way that it can be reduced to less than a carbide cutter cost. So it is good enough for the end user. Okay, for Yu Li Hong, as I can recall, there are special programs to create two pass for mirror finishing. Can you share with us? I think this is a very difficult topic to explain at this moment, but just for introduction is actually whereby certain mirror surface finishing like lenses, they can be non-circular, uh, or spherical or something like that. So actually what happened for the designers that are designing the lenses, it is actually based on formulas. For example, like x equals to what, y equals to x squared plus 3, something like that. So what happened for the FFCam is we are able to do so. We are able to get a very good model accuracy. We are able to put our cam tolerance to 0.05 microns plus minus, that means it's 0.000005, provided that your cam system and computer can take it. We need to put to decimal point of 5 decimal points. So, and the AP is actually 5 microns or 3 microns. So the total size can be in megabytes, many megabytes. Sometimes it can be point something gig. So for FFCam side, if you are doing something special shapes, FFCam is still an important requirement. But if you are doing some certain lenses whereby formula are related, then we actually have certain supporting tools from Tokyo that actually can help to create a two pass, which is much more better. And the key point for this is that because when you are going down the lens, you are actually cutting smaller and smaller and smaller circular paths. So feed rate has to be better controlled again and again. So these tools itself and applications can help to come up with this kind of special programs for better surface finishing. Yep, that is all. Is there any other questions? I think what is important here is we need to make sure that when you have this kind of inquiry in your regions, please understand that Makino is able to do to a certain extent. And based on these several case studies, you can actually do a little bit of a judgment to say whether we should commit this with the application, do a certain discussions, and then yeah, that's it. And then for the application engineers side, definitely we will try our best. If possible, we can have a collaboration once the pandemic is over, when guys can actually come over to Singapore or even to the Japan headquarters. We can actually do the test cut together so that the regional application
ஒரு நாள்
engineers can
அப்ளிகேஷன்,
learn.
ஒரு நாள் வந்து ப்ராடக்ட்.
Raja, yes, any question?
ரெண்டாவது நாள்.
Okay, so for Sudhaka, same question as per one of the guy, Vijaya. How much step over is used for PCD ball? Case by case, depend on the material. Sometimes we not only do for ferrous materials, we also do machining for carbides as well. So step overs varies. This is like as per normal machining conditions, but step over is never as much as 5 microns currently. If you're talking about certain like non-official market selling PCD balls at R2, R4 in China markets or something, then step over can be bigger. The grade itself is not that high as well. Okay, for you, Li Hong again, estimate how much should customer invest for milling mirror surface, machine cost, option cost, tool cost. Well, this is a very big topic to say. So I think we have to sit down and discuss with sales about the ROI for customer, what kind of part they are doing per part cost, and then tooling is definitely not a big problem because if you can do chewing, you can recycle the tools again and again. The main thing is only on the semi-finishing for certain parts whereby you need to make sure that uniform tool cost is the uniform stock allowance is being controlled. So you need how many CBN toolings. So that is the cost that's coming in. So for example, based on a particular test cut that I did for customer, 60 to 70 hours of cycle time, I was spending around like maybe 12k Sing dollars tooling costs. Machine costs, depending on the options that they are trying to get. For example, they get a air turbine spindle option, then of course it's more expensive. So this one have to discuss with sales. And finally, last but not least, customer need to understand that if they are doing certain special applications that they are willing to invest, they need to also consider metrology systems because these are also important to make sure that they know how they can achieve this thing. Same thing, the machining environment is important. We need to make sure that they have a facility that is well provided for the IQ so that thermal stability within that room is well controlled. Then we talk about inside. So normally if we are talking about plus minus 3 to 5 degrees Celsius for a particular room, internally is actually very hard to control. It can be like plus minus 1 degree Celsius, and plus minus 1 degree Celsius for that particular part will cause 1 to 2 microns or even 0.5 microns error. This actually will bring back to the final cutting process. Maybe some part is not being machined or something like that. So normally what we would recommend is that the environment should be plus minus 1 degree Celsius so that internally the chamber itself it should be plus minus 0.1. We also have cases whereby customer is controlling plus minus 0.2 such that the machining chamber, the internal space, is well controlled within plus minus 0.05 degrees Celsius. So it really is case by case to what kind of accuracy that the customer would like to have. I hope this answer your question. Any other questions? So just to summarize again, in overview, I hope that you guys actually understand that mirror surface machining by direct milling is possible. Okay, actually it's to a certain extent. In terms of like if you're talking about ribs mirror, of course it's not possible because this kind of tooling is not available in the market. So normally what application engineers do is first we analyze the geometry, then we will determine what is the final finishing cutter that we need to use, whether to use MSFS or not, because certain tools that is too small might not be applicable to MSFS operation. So this also means that it's a one-off product. After using, we have to scrap it. And then secondly, after determining the tooling and all this, we need to make sure that we get a very good finishing tool pass via the CAM systems. So this is the overall view. And the more information will be shared to the regional application engineer if you actually have this kind of information or customer inquiry. Then we will work together to understand this, because this is actually, even though it's a milling process, but because of its strict tolerances, the overall concept is almost opposite to the normal 3-axis milling process. So I would advise that if there is this need, then we will actually proceed with the actual application training. And for those who actually wanted the PPT, normally we will not share it unless of certain reasons. Please get your country regional heads to send an official request to us before, and the reason before we actually share it to you guys. Please understand. Yep. So as what Mr. Lim Zhiwei has already created this poll, for those that are actually able to do so, kindly try to submit your votes, because we want some interaction to make sure that you are actually listening to this overall session. Okay, so meanwhile, while you are doing the voting, please, if you have any other questions, you may feel free to ask me. From Sudaka question, for PCD mirrors, finishing coolant is recommended or not? Of course, coolant is also important, and we've tried several grades, and then we do testing, and of course, coolant itself is not that cheap, so we are unable to test different types of coolant to know which is evaluated to be the best coolant as among all. But we tried those neat oil coolants. We tried semi-synthetic oil as well, but the overall view, neat oil is recommended. Is there any other solution available in competitor machines like tool chewing, or how they are managing without chewing procedure? This question by Tamil Savan. Very good question. As what I've mentioned again, this MSFS tool chewing method is patented, so other competitors are unable to follow. So, okay, there might be many kind of solutions in competitor machines that we might not be having as well. So it's case by case. There are many new technologies in recent years, even ultrasonic, elliptical vibrations, many ways of cutting with different kind of tools. But this is by far one of the most easier method of machining. Okay, please submit your vote, everyone. I believe the participants is like 33. So I should have more than that. Kindly submit the vote if you are able to do so. The main reason why those that are unable to do the comments and voting is also because of the privilege rights that's been restricted, because if you are not a member. So in this case, for people who wanted to ask questions and you are unable to do so by typing, you may unmute yourself and pose me the question. Any other questions? Actually, not only ball and mill, we have PCD flat and mill as well. So for certain shapes, we also have radius and mill, flat and mill to do certain cutting, but the drawing is very difficult and we do not recommend it. And then the machining parameters is a little bit different again because we are not rubbing in a way of a radial method. We are actually rubbing in the actual method, so there are a lot of vibrations easily occurring when doing like a end mill application using PCD tooling. Okay, from Yu Li Hong, any case study on flat surface mirror machining, ball and mill, flat and mill? Currently, no. But test cut, yes, we did certain tests. Sometimes machining, we can say that machining is much more stable for ball and mill rather than flat and mill. Another key point for flat surface mirror machining, you know that for ball and mill, we are usually using the two tip. So overall surface finish results will not be very good. So there will be different kind of methods that we actually would suggest customer either to change a tilting angle for their lens using certain angled fixtures, or maybe with really no choice, uh, we have to implement certain other methods, which is much more complicated. So I think, yep, no case study for now.
Hello, Chu.
Yep.
Yeah, I want to ask you one question for the tape ball, ball and mill. The color sizes are I think 10 micron or 30 micron. For those kind of the small radius, can use the MS-FS to do the grinding or just one time use?
Okay, for this kind of table ball, first thing first, if you were to buy from the makers, they can do it for you, but normally the error will not be so small, maybe error 0.05 or something like that, and the taper is of a certain angle that you desired. So the making part takes a long time, 2 months, 3 months maybe for them. But for for our MSFS, what we do is we actually do it in a way we key in the formula, the angles, and the radius. We are able to do it, and based on that, we are able to further through it. So it should not be a big problem. The challenge is only that we need to make sure we measure directly, accurately using metrology systems to understand that when we say it is 35.2 degrees, in the measuring system is also 35.2 degrees. It cannot be bigger or smaller because this means that we are cutting more, and this will damage the thrower wheel and the cutter as well.
So I mean for the tape and the radius can be tuned together, is it?
Yes, one shot. Actually, it really depends on the size and the angle, because angle have limitations. If your angle is more than 30 degrees or something, it's easy for interference relief for the thrower wheel. If you are talking about 10 degrees, then it's not possible. First thing first, the cutter is like a thin whip.
Okay, thanks, sir.
Yep, welcome. Any other questions?
The next.
Hello?
Yeah.
Can you say it one more time?
Okay, what's the device to measure the mirror surface roughness?
First of all, we will not use the contact type measurement tools because this will stretch the surface. So we have to use optical methods to measure it. In certain companies and also in Makino Tokyo, we are using Zygo. If I'm not wrong, it's a German maker plus America collaborated group or something like that. It's a Zygo Emetec that we actually use to measure. So different scope is actually used, and also some computation methods are used to derive the profile shape to actually get the accurate surface roughness that you want. That is neglecting the profile projection.
Okay, thanks.
Yep. And maybe the cost of this machine is higher than the IQ machine.
Okay, I see.
For Lee Santa Maria, you say, does customer need a very good brain like yours? Actually, my brain is not that good, but we actually definitely will provide minimum required level of application not training to the customer such that they are able to handle this machine. Of course, from region to regions, there might be customs and habits by the customer, so we have to make sure that they ensure the SOP in order to achieve this, which is possible actually. In fact, we have a good case study in Thailand as well. Customer is using IQ 500, and maybe for the first few rounds it's very difficult, but the application engineers are going in few times frequently to actually let them understand that the process has to be improved, the way of doing has to be changed. Yeah. For Chaitanya, for IQ machine series, what does IQ means? Actually, I'm not very sure. I think it's required to certain intelligence. And respond back to Yuli Hong, very important. Yes, the attitude of operating is important. So sometimes when I was talking about, please do a calibration of the AWM using the ring gauge. So the way of doing the AWM, they just simply put it on a magnetic stand and just place it in and do the calibration. So when I say, how is the flatness of the ring gauge? They say, should be good. But if I enforce them to measure, it is like 50 microns out. So this also get back to the point whereby if the flatness is no good, the AWM is out, the everything shift by a few microns. So attitude is very important. So now It's already 12 p.m. Singapore time. Is there any other questions? Final reminder again for the sharing session, PDF and a certain PV value document is uploaded into the files tab of this channel. If you wanted the PPT version, please state a valid reason to your regional heads and let your regional heads send an official request to us. Okay, thank you.
Okay, guys, if you don't have any questions, we will end our session here. Write your questions. Just a reminder, the next session will be on 9th of April, 10:30 a.m. The topics will be on introduction of a CSG, collision safeguard. Introduction of CSG, collision safeguard, 10:30 a.m., 9th of April. Please share this link with your friends and colleagues if you think that this might be a topic they will be interested and they want to learn from it. Thank you.
One more thing to add on is not only this CSG learning session on the PM online sharing team, there's also another 2 more channels. So there's this mutant learning session by Raja. So if you guys are interested, please also log into this channel. Okay, if there's no much other questions, then we will end this learning session. Okay, have a good day and stay safe. Bye.
I will put the link for the mutant session in below. So you guys, if you want to attend the mutant session tomorrow, please click on the link. The link is as per attached. Please join the link if you guys want to attend the mutant session tomorrow, 10:30 a.m. 10:30 a.m. tomorrow.